This is problem 18 from chapter 15. In this problem, two disks, A and B, each have a mass of 1 kilogram and the initial velocities shown just before they collide. If the coefficient of restitution is 0.5, determine their speeds just after the impact. So puck A has a velocity of 4 meters per second in the negative y direction, and puck B has a velocity of 3 meters per second in the positive x direction. Now, one thing that we have to note from this figure is that the line that they show us here is the plane of contact. Perpendicular to that line is the line of impact. And they give us the coefficient of restitution, and the equation that we have, which is 1511, for the coefficient of restitution uses the components of the velocities along the line of impact. So I'm going to need to find those components. The line of impact is perpendicular to the plane of contact, so that's perpendicular to the line that they gave us on the diagram. So here, this is the line of impact. So I'm going to have to find the components of the velocity which are along that line. Now, they told us this was a 3, 4, 5 triangle, so let's call this angle here theta. If this angle is theta, this angle is also theta, and this angle is theta, and this angle is theta. If this angle is theta, the adjacent side is 3. So if I'm going to break this velocity down into components, I need the component along the line of impact. And since they already called this x and this y, let's call this x prime and this y prime. And so we're going to break this velocity of 3 down into an x prime component and a y prime component. This is a right triangle, just like this right triangle here. If this is our angle theta, the side which is proportional to 3 is adjacent to that. So this would be 3, this would be 5, and this would be 4. And if we want to break the velocity of puck A down into component x prime and y prime components, you would do it like this. This is the y prime component, this is the x prime component, this is a right triangle. Since this angle is theta, this angle is 90 minus theta, so this angle is also theta. The side which is proportional to 3 is adjacent to theta, so this is 3, and this is 5, and this is 4. So now we should be able to break our velocities down into components using what we have here. So for puck A, I have a velocity of 4 going straight downward. Then I have my y prime component and my x prime component. So if this side is proportional to 4, this side is proportional to 3. So if this is 4, this is 3 times 4 divided by 5, and the x prime component is 4 times 4 divided by 5. For the velocity of puck B, we would use this triangle here. The velocity is 3, and the components in the y prime and the x prime direction I'll find by using this triangle here. So this side is proportional to 4, so if this is 3, this is 3 times 4 divided by 5. This side is proportional to 3, so that's 3 times 3 divided by 5. So this is the positive y prime direction. So this is in the negative y prime direction, and this is also in the negative y prime direction. So I have to add this and this together to get my initial velocity. So this is VA y prime before the collision is the component that I have here. That's in the negative y prime direction. 3 times 4 is 12. So that's minus 12 over 5. This is the y prime component for puck B, which is also in the negative y prime direction. So VB y prime before the collision is equal to negative 12 over 5. And let's put down the x components also. Before the collision for puck A, the x component is what we have here. It's going this way. This is the negative x prime direction. So that's negative 16 divided by 5. And for puck B, that's what we have here. That's the positive x prime direction. That's 9 divided by 5. So all of that was just breaking the initial velocities that they gave us down into components. We had to do that because we're going to use the equation for the coefficient of restitution where the components of the velocity are along the line of impact. So that's why we needed to do that. But there's another advantage to doing this. In addition to the equation for the coefficient of restitution, we're going to do the conservation of momentum. The conservation of momentum is a vector equation. I can use this equation in the x and y directions or in the x prime and y prime directions. And if I do it in the x prime and y prime directions, I have the two pucks here, and the normal forces are along the line of impact. So here are my two pucks, which are supposed to be touching each other. And the normal forces are like this, along the line of impact. If I look at the system as a whole, the total impulse that I have is 0. But if I look at just one puck, so this one is puck B, and if I make my system just puck B or just puck A, during the collision, I have a force acting on B along the line of impact. I have a force acting on puck A along the line of impact. But looking at just puck A or just puck B, the impulse in the y prime direction is 0. So the force is only in the x prime direction, so there's no impulse in the y prime direction. If there's no impulse in the y prime direction, using our equation for conservation of momentum for just one puck in the y prime direction, if the impulse in the y prime direction is equal to 0, the mass times the velocity before is equal to the mass times the velocity afterwards, which means that the y prime components of the velocity are the same after the collision because there's no impulse in the y prime direction. Okay, so we got that taken care of. So that was conservation of momentum in the y prime direction. We can also do conservation of momentum in the x prime direction. Rather than looking at the two pucks separately, we can look at the two pucks together. So if this is our system here, the impulse is equal to 0 for the system because these forces are equal in magnitude and opposite in direction. So using the conservation of momentum in the x prime direction, we have the initial mass times the initial velocity of puck A in the x prime direction plus mass B times the initial velocity of puck B in the x prime direction. Since there's no impulse, this is equal to mass A times the final velocity of puck A in the x prime direction times mass B times the final velocity of puck B in the x prime direction. Since we did all this work before, we can go ahead and plug in our numbers. The mass of A and the mass of B is equal to 1. So we're just plugging in what we have here. This is minus 16 over 5. This is plus 9 over 5. This is equal to, oh, this is, why did I have y prime here? This is x prime. Okay, so this is VAX prime 2 times 1 for the mass. And this is VBX prime 2 times 1 for the mass. Okay, so this is equation 1, let's say. My other equation is going to come from equation 15-11 for the coefficient of restitution. They tell us that the coefficient of restitution is 0.5. The coefficient of restitution is for the components which are along the line of impact. It's the difference of the final velocities in the numerator and the initial velocities in the denominator, and whatever object comes first in the numerator does not come first in the denominator. So let's put a first in the denominator. So this would be minus 16 divided by 5 because that component is negative. And then it's minus VBX prime. So it's minus 9 over 5. So in the numerator, it's VBX prime. This is after the collision. Minus VAX prime after the collision. And this is equation 2. So let's go back to equation 1, and we have negative 16 divided by 5 plus 9 divided by 5, which gives us negative 7 divided by 5, which is equal to negative 1.4. Then for equation number 2, I have negative 16 divided by 5 minus 9 divided by 5. Negative 16 minus 9 is 25, so that's negative 25 divided by 5, which is 5. Then we bring it over to the other side, and it's still negative, and it's negative 5 times 0.5, which is negative 2.5. And now on this side, we just have VBX prime 2 minus VAX prime 2. Okay, so now we have this and this. My favorite way to solve two equations and two unknowns, if I can, is to just add the two equations together. And in this case, if I add these two equations together, since this is a negative VAX prime 2 and this is a positive VAX prime 2, those will cancel out. So add 1 and 2. And when I do this, I want the negative 1.4 to be on the left-hand side. So it's negative 1.4 plus negative 2.5 is equal to what we get when we add this and this together. The VAX prime 2's cancel out, and we have VBX prime 2 plus VBX prime 2, which is 2 times VBX prime 2. When I solve this for VBX prime 2, I get VBX prime 2 is equal to negative 1.95. And I can take that and put it back either into equation 2 or equation 1, and I get VAX prime 2 is equal to 0.55. So now I have the final components for the velocity in the x prime direction. And I already had the final components for the velocity in the y prime direction because they don't change because there's no force acting in the y prime direction. So to finish this up, I was only asked to find the speeds. So I can add the the squared of the x prime component to the squared of the y prime component and take the square root, and that will give me the final speed. So for puck B, I have 1.95. It's negative, but I'm squaring it, so that doesn't matter. And the y prime component is negative 12 over 5, and I'm squaring it, so it doesn't matter that it's negative. And this gives me 3.09. And for puck A, I have 0.55 squared plus negative 12.5, which I'm squaring. So let's say 12 over 5 squared, and this is equal to 2.46. And the units that we have here are meters per second. So there we have the final speeds. Okay, so the important thing to remember from this problem is that when you use the coefficient of restitution, it's the components of the velocity which are along the line of impact. So we had to use a different coordinate system here to find the components which are along the line of impact. And since we had to find the x prime components anyways, we did conservation of momentum in the x prime direction and in the y prime direction. And the advantage of doing the y prime was that there's no force acting in the y prime direction. So that concludes fundamental problem 18.